Okay, so I'm gonna have a little bit of a rant about sort of computer architecture and sort of on the bottom bare metal stuff. And I'm just saying this because I've literally been stuck on it at work and I can't get my head out. So this is something that's bothered me for a while now, is that pretty much all computers that are used today, like account of this von Neumann architecture. So the idea is that you have these sort of three systems. You have like the memory, you have the controller, like it says it like it tells what to do, and you have the ALU. This is like the thing that does the math. And sort of data is passed between the ALU and the memory, and then they sort of do this dance with the controller to like execute all your programs. Um, and so von Neumann, it's really old, right? Like von Neumann was an old guy. I can't remember. It was like 20s or something. And it's just kind of been iterated upon, iterated upon, iterated upon with all this sort of engineering. I don't want to call it nonsense because it's really good work, but it makes the whole CPU and everything just so goddamn complex. Like here's like some of the things that engineers of the von Neumann architecture do to like fix things up. So they first off they do multi-threading and like multiple CPU cores and stuff to like try and like separate out concerns so that computers can run more things around. They do these things called SIMD instructions where sometimes you'll throw an instruction into the CPU like, hey, add these 100 numbers together, and it will treat that exactly like one instruction, because if you repeat the CPU over and over again, it'll be slow. They do stuff like pipelining where they throw like many instructions in at the same time. And they do stuff like branch prediction where like things branch off. And basically, I hope you're understanding that this is all just sort of hacked on to this really old architecture that sort of no one's changed, if that makes sense. And then another last thing is this memory loading. It frustrates me a lot because I'm pretty sure this quote, I don't know where it is, I have to track it down, but like apparently loading the memory to the ALU is by far the most expensive sort of instruction. Getting it all the way from the RAM, all the way from L4 cache, all the way down is what's actually expensive. So I just get like really annoyed. I'm like, there has to be a better way. And of course, like there are other architectures, like there's data flow computing, which is like the closest thing to what I'm about to talk about or suggest. And like, obviously there's GPUs when the problem is sort of like embarrassingly parallelizable. I think that's the actual term that computer scientists use. And these GPUs are like, and these are all really great when you have like specific problems, but I would really love to just build an architecture that will sort of just handle it, like be as parallel when you want it to be parallel, and as sort of single threaded when you need it to be. And so what would our dream architecture actually be, right? Like first of all, it'd be like it naturally parallelizes. So like when it's got a program, it'll throw like, and it sees like 15 instructions it can do in a row when none of them are dependent on each other. It'll just go ahead and do all that and not worry about it. But ideally, this doesn't happen with a huge cost to like single threaded. Ideally, it would be able to just go and do like 20 instructions in a row and not spend all this time doing calculations that don't make sense. This is the biggest thing, right? That bothers me. That needs to be like more simple to implement. Like I have like with modern CPU architectures, it just seems insane what they do. Like for branch prediction, which is when a program has a fork and it can do one thing or another, like if it like a giant if statement or something. They literally have like what amounts to small neural networks just like embedded in the chip to sort of work out which one's going to happen. And sort of an important thing is that this like a new architecture that would be backwards compatible. So it has to like work with all the pre-existing code that's written in x86 and ARM and all that. So this all started when I was listening to talk about the Apolo computer. So the Apolo computer worked more or less like a normal von Neumann computer that I showed at the very start. If you wanted to save something in memory, let's imagine you save one to save it. It comes out, and if you want to read again, you can read that out, and you can see. So this wouldn't be here anymore, and you just be, and you'd be able to read out the memory that was in that cell, and everything changes. But what was really interesting about it is, in a way to like augment their instruction set, little special registers that they would write to. So if you write 0, like 1 to the special register, and then you'd read it out, it turns out this special register would do like a left shift operation. So you'd read out like 000 blah 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 10, And that saved the CPU from having like these extra instructions that like in Apollo's time were really expensive and complicated to input, but you still had sort of the ability to do this math. My sort of thought was, is like, what if we ran every operation exactly like that? Like, get rid of this ALU. All the processing happens in memory, basically, like right next to the quote unquote RAM. And then we just have a controller just says what instructions should this memory do. Um, and and so ideally, like every single memory instruction is, and so ideally every single instruction is just read from this address, write at this address, and the address that you write to might have some processing with it. Maybe it won't, it might just be moving memory around. But ideally is that like as these addresses move around, computation gets done. So yeah, so that's the thing. Every instruction is just simply two small parts. You read from address A, you write to address B, and computation gets done. So here's it. Like the number 6 gets saved, the integer 6 might get saved to address 01, and this might have the special purpose of incrementing the value. And then when you read from 01, you get 7. So yeah, I really want to emphasize, this just started as a joke that I thought in my head. I was like, that'd be pretty funny. But then I started thinking, like, if you didn't put everything on the same bus, so all memory wasn't dedicated to like one output, you could parallelize this thing, right? So for example, like multiple operations could occur at the same time. So you could have like as long as the memory wasn't using the same bus, you could have addition on this part of the chip and then multiplication over here and then bit shifts and like read and writes, etc. and blah, blah, blah. And like that would save you like all this engineering effort that these x86 that we were going over before, that like these von Neumann engineers are following through, is like can be sort of thrown away because it's all just parallelizes on the chip. Another thing is instructions never get more complicated than read from X and write to Y. So x86, it actually has like something up to 128-bit instructions, and these have like composed of many micro instructions that encode for various operations that can happen in a single clock cycle. And this is what I'm talking about when I'm just drowned in complexity when you look at modern architectures. And then memory loading. So memory loading is a huge problem, but like the idea is you can design the trip so that the memory gets loaded to the places where the data is put. So I started like tinkering at this, and I was like, oh no, this is going to take up my brain. So this is just the first iteration. I'm sure that if anyone did anything with this, it would be completely different and be virtually unrecognizable. Something like this, okay? So we have basically a binary tree of buses that all lead to a bunch of different memory addresses, okay? And then you just have a controller off to the side. I have thought of ways of maybe implementing this into this, but into the actual memory at the bottom, but it doesn't matter that much. And simply all it is just 64-bit numbers. The first 32-bit numbers might be read from this address, and the second 32 bits of numbers would be write to this address. So for example, this instruction here would be read from address 3, so this one, and write to address 4. And the idea is the bus would just be would have a bunch of decision points at it, where like little switches, etc., transistors, etc., would flick on and off. So boom, boom, boom. And then you just control the bus so it goes all the way up and around. These buses get powered. In my head, I'm imagining this bus as like a 64-bit bus. You could do a serial bus if that turned out to be the best. I doubt it though. And then this can just go all the way down to like the memory 4, and it goes all the way around here. And the reason why you'd set up this like complicated nonsense is because then while this is going on, while this big read is going all the way around this thing, you can set up a much smaller memory, memory thing. So it goes just up here and down here. Ka-chow. And because these two buses aren't touching each other, there's no sort of red line that goes in between, these two things can happen at the same time. So yeah, so this one means read at sorry. Okay. And so the advantage of this thing would be like auto pipeline. So, and code compilers already do this to my understanding, is you'd see all the way here and go 03, 04, 02, 01, 02, 06, FA, 09, 00. Okay, so all these instructions are independent of each other, and it's only this last one that really matters. So, like, yeah, exactly. So all these first four instructions don't depend on each other. None of them save to another address that another instruction uses. So then you can just send these off to the CPU and say to the CPU or the memory or whatever you call it, and just say. So like, and then this instruction might get executed first and like get finished, and you get a signal back. Like obviously, there's lots of implementation details I'm glossing over here, but value might come through, and this value might come, and then boom, like this first operation that we've been waiting on to iterate through comes through. So now all these values have gone through, and because this operation is already done, you don't need to just iterate the next one. Take all the way down. Boom! Like now you're up here. This instruction is already done, so you don't need to recompute, and you can just keep the registers just going and compute that one. So this thing has just like so many advantages that you just see in my head. So like, first of all, you can optimize things at compile time. You don't need to do a lot of branch prediction and stuff. So you would build a chip to a certain geometric structure, and let's say the compiler knows that, okay, this part of the chip is really good at addition, at like vectorized addition, so we're going to save our memory there and there. And then you can also optimize your compiler for like smaller distances. So like memory moves the least amount of distance. It's not going all the way up to the top of the tree that I showed and then all the way back down. And then you can like optimize it so the memory doesn't spread out. And you can do this all sort of analytically at compile. So branch prediction can also be done, quote unquote branch prediction, because all you do is just have let's imagine you have two branches going through. What you have to do is have these two sets of instructions and interlace them. And as long as you'll be careful with your branches that they don't save memory to the same place, they should just be able to execute at the same time while you're waiting for different things. This is even if you need branches. I can totally imagine the counter will be taking time. I could totally imagine scenarios where this architecture is implemented that doesn't have branch prediction, but this is just sort of a way you could implement it if you wanted to. So the idea is like, even though the CPU in inverted commas is just seeing a list of instructions, it knows that none of these are dependent on each other. So it can sort of analyze this by itself and analyze this by itself. And it just sort of runs these two programs at once and can throw it out if it doesn't like it. Yeah. This architecture, I don't see why you shouldn't be able to make a transpiler. So already compilers, they sort of reorganize instructions so that they can take advantage of this like crazy von Neumann architecture that people have come up with, so they can parallelize as much as they can and run like 4 operations at the same time. So the idea is that you could just sort of build this chip, and then there would be no barrier really to making it. And then and frankly, like, this doesn't stop here. If someone writes a program specifically for this chip, you could foreseeably see reasonable gains, but like everything that works still works, and anything that's designed for this chip will work better. And I can imagine you could build this chip that basically emulates an x86, so there's no issue. So it's exactly the same performance as an x86. I think that's a. This is an interesting one, and I might be wrong about this for some complicated like OS reason, but you shouldn't really need cores or threads, and you can sort of virtually implement them. So rather than having to manually specify, if you just put memory of like this task over here on the operating system, and you put memory of like this task over here, they should never ever interact, as long as like, this is CSGO and this is like, Windows like update or something. As long as it doesn't try and read a memory address from CSGO, which it should never happen, these two things are going to be able to run in parallel just fine, and you should be good. no cache misses, because in this architecture you shouldn't, famous last words, need a cache. And frankly, you should be able to just save your programs in the places on the chip where the arithmetic sort of memory spots are the most useful. So maybe not no cache misses, because the equivalent would be being at one part of a chip over here. Let's imagine. Yeah, I'm trying to work out how to draw, but that's okay. Would be having one part of the chip over here, and you wouldn't be able to, and that has like arithmetic logic units and stuff, and the other part of the chip like over here, who has like a bit shift operation or something, and then you have to move all the memory over, but that's fine. A problem that you can see is that like different chips would need different instructions, because you might not necessarily, one manufacturer might put like address 01 is the bit shift operation, and another manufacturer might be like, oh, address 01 is the is a zero register where just everything's zero. So you will probably need something like a compatibility layer before you compile. So you compile to some general code, and then this compatibility layer runs at compile time or at download time, etc. And this is yeah, and this would be our solver. I don't imagine this is the end of the world, but obviously it's not ideal, but this can happen. So the most interesting thing about this is, and it's something I wonder about a lot, is it's a much more customizable chip. So if you think about it, modern CPUs, etc., are pretty much just focused on speed, on just instructions per second. And I find that quite odd, because I feel like there's a very different workload to a Photoshop workload, to a like a gaming workload, to a like a video encoding workload, and different chips have different speeds, etc. Like, I'm aware of that, but they're a lot more correlated than I thought they would be. And I imagine that like in this sort of reference frame, you would be able to make chips that are so much more customizable to specific processes. So it might be blazingly fast at Photoshop and quite slow at Blender or something, depending on what you add and how you optimize your chip. And sort of the only way you really have to build different computer for different workloads is like an x86, and then you put some coprocessors, or you add a video encoding module onto it, or you do some stuff. And there is a little bit, obviously I'm glossing over a lot more, but hopefully you can understand that like this thing can just be done to the like wazoo, be changed, and yet it will still be able to run just sort of basic programs. So it won't break anything in the past, but we'll be able to parallelize. I think the last thing, the slide that I actually skipped over there, was you shouldn't need a GPU with this chip, if I do this right. So you should just be able to say like this whole part of the chip over here, it has a bunch of matrix multiplications, which will read from like these rows, which will read from these memory addresses, etc. And you should just be, and because all these sub buses are quite small, and can go between each other really quickly, you shouldn't have that much of a problem with like just implementing the type of stuff that GPUs are really good at just on your CPU, quote unquote. And then over here, you might have a little part that has lots of like addition and just all the general logic that a CPU needs. And these two can just sort of communicate with each other, and the optimizer can just like run at compile time, and you shouldn't need to worry about sort of importing a shaders language and doing all this stuff. I mean, you will have to worry when you write your code that the compiler and interpreter can understand everything, but it should be good. And I don't know, this has just been driving me crazy for the last week, and I just needed to get out my thoughts. I don't know. I'm pretty sure someone can probably tell me why this doesn't work, but I think for now, it's just a really interesting idea, and I kind of want to pull that thread further, but I don't really know how. Yeah. Um, how do I stop recording?